we're going to be looking at how we can extract metals from their ores. The first thing we need to understand is what this word ore means. And it's a rock that a metal can be extracted from for profit. So lots of rocks have amounts of metal in them. If that amount of metal is large enough, then we can extract the metal and purify it from that rock. And obviously there's lots of metals that are very important in our lives. Copper for wiring and as a conductor, iron for building, aluminium for building lightweight materials. So ores and therefore rocks are very, very important in our lives. Ores, there's lots of different types of ores, but there's some common ones that we need to know about. One of them is bauxite, which is aluminium oxide. So what we can see is that the aluminium is chemically combined in a compound with oxygen there, and we're going to need to do something to get rid of that oxygen. There's one of the iron ores called hematite, which has the formula Fe2O3, so it's two iron atoms and three oxygen atoms. Then we've got a cassiterite, which is a tin ore, so Sn is the symbol for tin, SnO2, cuprite, and these are just some examples of the different types of ores that exist. And the key thing here is that they all are combined with oxygen, chemically combined with oxygen. So if we're going to get a useful metal out of them, we need to find a way to remove the oxygen. And there are different ways of doing it. The oldest and most common way is the way that we're going to have a look at today. So let's have a look at how we could extract lead from lead oxide. So lead oxide, most lead ores are actually not oxides, but this is a good example. So lead oxide we can think of as being an example of an ore. Now, if lead oxide is heated with carbon, a chemical reaction takes place that produces lead and carbon dioxide. It's a little bit easier if I actually look at the symbol equation for this. So the symbol for lead oxide is PbO2, which means there are two oxygen atoms connected to one lead atom, or in fact two oxide ions and one lead ion. When that reacts with a carbon atom, the carbon is more reactive than the lead. So the carbon displaces or takes the oxygens from the lead to make carbon dioxide. And what we're left with is a lead atom. And obviously this happens millions and millions of times, and we end up with lots and lots of lead atoms. So the key thing here is that the carbon is more reactive than lead. And therefore it displaces the lead, and we're going to see in future lessons what this word displacement means and the chemical reactions that take place. We need to be able to describe what's happened to lead and what's happened to carbon. So in terms of oxygen, lead has gone from lead oxide to lead, so it has been reduced because it has lost oxygen. In previous lessons, we've also seen that we can also describe something being reduced as having gained electrons. That's not too important for this lesson, but it is an important fact for us to remember. Carbon has been oxidized because it has gained oxygen. We can also say that it has lost electrons. So let's have a look at some more examples. But actually, just before we do that, what we can say here is that the metal ore has been reduced with carbon. Right. So let's have a look at some examples of chemical reactions with metal ores. So copper oxide, first of all. If we heat copper oxide with carbon, then we reduce the copper oxide and we're left just with copper, and carbon dioxide is produced. If I was going to write a simple equation for that, CuO plus carbon goes to make copper and carbon dioxide. So the formula for copper oxide is CuO. Obviously, this equation would need balancing, so I'd need to put a 2 in front of there and a 2 in front of there to balance it. Again, we can say that the copper has been reduced because it's lost oxygen, or it's also gained electrons, and carbon has been oxidized. Let's have a look at one more example. Our example of hematite, which is iron oxide. So again, the same thing is going to happen. Iron oxide plus carbon. The iron is reduced to make iron, and the carbon is oxidized to make carbon dioxide. So we can say iron has been reduced and carbon has been oxidized. If I wanted to do this as a simple equation, it's a slightly more complicated one because it's a tricky one to balance. So that's the simple equation there. Fe2O3 is the formula for iron oxide. To balance this equation, I'd need to do this. Now, it's important for us to realize that some metals are very, very unreactive, particularly gold and platinum, and to some extent, but not always, silver. So these metals are very unreactive. If they are unreactive, they're actually often not found in the ground, in rocks, in ores. So they are often found native in the Earth's crust. So what that means is not as an ore. Thank you very much.